to take questions along the way, and I think you can just write them into your chat box there as you see the need to. Where do we use them? Well, accelerometers are really meant to be used with machines that have rolling element bearings in them. That's because we're measuring the transmitted vibration from inside of the machine to the outside of the machine through the bearing or through the casing of the machine. And as you can see here, we can take this transmitted vibration up into the accelerometer and simply convert it to a voltage, 100 millivolts per G, let's say, and then pass that along to our data acquisition system. And this is a measurement of the absolute vibration of the machine. So we are measuring the absolute vibration with our data acquisition or condition monitoring systems. Typically, we would mount the accelerometers in the vertical location and the horizontal location, and those would be our radial measurements, primarily the lower frequency measurements. And then also we would have an axial measurement, and we'd like to have this axial measurement in the loaded zone as much as possible. We'll get the most out of our measurement if we can keep the axial measurement in the load zone, and probably we'll also get the higher frequency faults here in the axial direction. What are the advantages of an accelerometer? Well, it measures the casing vibration. It measures the absolute vibration. You can integrate them to velocity. In fact, I would say probably 99% of you are doing that now. You're using an accelerometer in your hand, and you look at your data collector, your condition monitoring system, and you're measuring velocity. They are relatively easy to mount. There is a large range of frequency response, and they do come available in many, many configurations. Where not to use them? Fluid film bearings. Our fluid film bearings have got oil in them, as outlined here by the orange, and because of that oil, they have a large damping. So that oil is providing damping, and the vibration of the shaft does not transmit very well to the outside of this machine case. In fact, maybe the first measurement you get with an accelerometer is when the shaft actually hits the case of the machine. So be very careful on a fluid film bearing. Know that you're not going to get the true amplitude because of the damping of the fluid there. Disadvantage of accelerometers: they don't measure the shaft vibration as we've just seen in that fluid film bearing. They're very sensitive to mounting techniques and surface conditions. We need to have a really good mount so that we transmit that vibration into the sensor. It's difficult to perform a calibration check. You need a nice shaker and good mounting methods and good accuracy on how you measure that output. And of course, one accelerometer doesn't fit every application. So you should have a series of different accelerometers for different applications. We can see here that we've got accelerometers mounted on our motor. This is in the vertical direction, and also on our fan in the horizontal and in the vertical direction. This is typical of what you'd see on any motor fan unit. Here we've got a pump, and this pump actually has pre-existing mounts on it. These are quick connects, so that for a portable data acquisition system, you can simply connect to the landing target that's on the pump. And this is a wind turbine, one of the newer applications, if you'll have it in the last, probably 5 years. But we've seen a lot of renewable energy come around, and wind turbines is part of that. And you can see here on the gearbox, we've got our accelerometers mounted both vertically and horizontally, and also on the main bearing for the big prop out there. So this bearing is probably a meter in diameter, and we've got our low-frequency accelerometer mounted here in the horizontal direction. We do have a very nice brochure that's available as a PDF. It talks all about the industrial accelerometer and many of the things we're going to cover here today. Certainly, if you want to leave your name with Matt, he can get these out to you they can be just sent over to email. Looking at the construction of an accelerometer, we'd start out with a pedestal or a post. This is going to form our basic building block for our accelerometer. And around that, we're going to put a PZT ceramic ring or a piezo ceramic element. So this is going to look kind of like a donut around this post. Then we're going to bring in our mass. So we have a mass here now. It looks like an inverted teacup sitting on top of the ceramic. We'll add our circuit board. We're going to do some charge to voltage conversion, and we're going to do some amplification here, treating the signal inside the accelerometer. Here's our Faraday cage. This is just like putting a can over the top of your sensing element. So this Faraday cage, when it comes into play right here, that's the first line of protection against electrical interference, any type of electrical noise you have. This can is going to cover up the entire ceramic and the electronic package and just protect it from all that outside noise. We also are going to put in an electrical isolator down here on the bottom because we don't want to form a ground loop here. So we're going to have an electrical isolator on the bottom of this sensing element. Then we'll pull in our 316 stainless steel housing. We're using an L version of 316 because it makes it weldable. We've now got a good solid chunk of steel or stainless steel around our sensing element, providing protection. We'll put our 1/4-28 threads in here, and we can have any number of adapter studs, M6, M8, M10, off this 1/4-28 base. And then we're going to fill the inside with epoxy. What we want to do is we want to keep everything centered, and we want to keep everything electrically isolated. So all this black area now becomes our electrical isolation from any ground loops. So this sensing element is totally isolated inside the sensor case. We're going to put on our hermetic connector. It could be a 2-pin or 3-pin or 4-pin even, depending on the type of sensor we're using. The important part here is that before we install this connector, we're going to bombard this sensor with helium. We are then going to weld this sensor closed. So we've welded this sensor closed. There is helium inside of this. The next step is to take this sensor and test for the leakage of helium. If it leaks, the sensor is discarded. If it does not leak, the sensor is hermetically sealed and exceeds IP68. So we are not only providing a weld, but we're providing a foolproof test that the sensor is hermetically sealed. Just as we look a little bit at our pedestal here, our post, and our ceramic and our mass, it's these three parts that really form the core of the accelerometer. The vibration is transmitted up through the post. The mass is trying not to move, and because of that difference in vibration and mass, you have a shearing mode taking place in the ceramic. So these are shear mode accelerometers, and the shearing of this ceramic provides an electrical charge. And that charge is converted to a voltage with this amplifier board right here. So the charge output of the ceramic is amplified and converted to a voltage by our integrated electronic piezoelectric circuit, our IEPE circuit. This is a standard 2-wire technology that exists all around the world and is used by all the major manufacturers of not only sensors but data collectors. Looking at our outputs, we actually have two outputs on an accelerometer. One, the sensitivity. This is the usable output. This is what you guys are using to develop your FFTs and your time waveforms. It's the dynamic AC signal. When we put this on a shaker, we would call this the calibrated output. It would also have a sensitivity tolerance. The other output is the bias voltage. Now, we don't use this to measure vibration, but we use it to judge the condition or the operational standing of the accelerometer's electronics. So a typical DC bias voltage is 10 to 14 volts DC. That indicates the accelerometer is simply turned on and that the electronics are operating. To test the sensitivity, we need shakers. To test the bias voltage, we simply need a power supply and a meter. So let's take a look at how we would test each of these. If we're testing a sensitivity of an accelerometer, or we want to check the calibration really, well, if we're working on very low frequencies, maybe I've got a wind turbine and I want to know what the frequency is at 1 hertz. I need a stroke shaker. And this is just like a hydraulic cylinder. And it strokes back and forth at a predetermined rate and amplitude. It also has a reference accelerometer mounted in it. So you can see our accelerometer will be mounted here, and it would be compared to the reference accelerometer in this head piece right here. And this is good for 0 hertz DC all the way to 100 hertz. Once we get above 100 hertz, we can switch to a dynamic shaker, as we've seen here. This shaker will actually go from 10 hertz to 50,000 hertz. So this does all of our high frequency testing, all of our engineering work for high frequency. It's an air-bearing shaker with a beryllium core, so it's non-magnetic and basically floating in air, and that's how you can get such a high frequency from it. So to test the sensitivity or to calibrate the accelerometer, you really need 2 different shakers. Now, it's a good rule of thumb out at the site or at the mill to have at least a single point shaker. And typically, especially in the metric system, that's going to be running at 159.2 hertz. And what that'll do is give you 10 meters per second squared at 159.2 hertz and allow you to see that one sensitivity. So that's kind of nice to have because it's a quick check type of device that you can use right at your site. Measuring the bias voltage, we would provide something like the TM1018 test meter. And what this meter does is it provides power to the accelerometer, and it checks for a open circuit, normal circuit, or short circuit condition. And up here in the panel display, it actually displays the existing bias voltage that it measures. So this is a very handy device. It's very good for troubleshooting. You can start right out if you have a switch box and connect this to the switch box. Now you're checking the switch box, the cable, and the accelerometer. If you find a problem, disconnect the cable and just go with the cable and the sensor. If you're still seeing issues, disconnect the sensor and just test the sensor. So a very good basic troubleshooting tool for electrical circuits and connectivity and just making sure you've got the power in the right place at the right time. Several different types of accelerometers based on the functionality, the durability, the affordability. Applications that we're going to do trending, alarming, diagnostics. And remember, one sensor doesn't fit all the applications, and a lot of that has to do with fit, form, and function. So we've got a wide variety of different sizes and shapes and outputs and frequencies and things like this, and should be no problem finding the right one for your application. Looking at some basic designs, our top exit, our side exit, our triaxial accelerometer. So you can see we've got 3 sensing elements in the same housing here. And of course, the dual output vibration and temperature sensor. So these are just 4 of the basic configurations that we could have. And we'll look a little bit on how they work and what the wiring might be. Each sensor comes with specifications. Those will be found on the data sheet for that sensor. And you'll see things like sensitivity, 100 millivolts per G plus or minus 5%. The frequency response at 3 dB and 10%. And maybe if this is a premium sensor like we're showing here at 5%, we'll see the dynamic range. How much vibration can this sensor have before it saturates? And what is the resonant frequency? In this case, it resonates at 26,000 hertz. If we have a 10 millivolt per G accelerometer, this is an accelerometer that's going to be used for something that's vibrating badly. There's going to be a lot of vibration. It's going to be very harsh. You might find this on a shaker screen. You might find this on a reciprocating pump because there's a lot of impacting on that recip. And the benefit here is that you have 500 Gs of dynamic range. So 10 millivolts per G times 500 Gs will give you a plus and minus 5 volt AC output at its maximum. The 50 millivolt per G sensor is well liked by NTEC Rockwell. They seem to have settled on this as their general purpose sensor, and I believe that is due to the 100 Gs of dynamic range. It still has a nice sensitivity and a little bit more dynamic range. It allows them then to have a little broader application possibly. Still though, 50 millivolts per G times 100 Gs is plus or minus 5 volts AC. So again, you'll have a maximum output of plus or minus 5 volts AC. This is the famous 100 millivolt per G sensor. As I've said here in the red block, probably 90% of all vibration analysis and data collection is accomplished with 100 millivolts per G accelerometer. This is the popular one, the big seller. And it does come in 50 G and also in 80 G dynamic ranges. So it could have a plus and minus 5 volt output, or it could have a plus and minus 8 volt output. So a little something to be aware here, that we do have two different ranges available, but they will also provide a larger maximum output if it's 80 Gs. And then for low frequency work, low amplitude vibrations where you need better signal to noise ratio, we have our 500 millivolt per G products, but again they'll only measure up to 10 Gs, and this is still latched on to the plus and minus 5 volt AC maximum output. When we're looking at frequency response, we're talking about the usable frequency range of the sensor when it is stud mounted. So the frequency response that's in the specifications is related to the sensor being stud mounted on one of the shakers. And the frequency response is always referenced to the actual calibrated sensitivity. So if your sensor is calibrated and it says it's 95 millivolts per G, then the frequency response will be referenced to that 95 millivolts per G. There are 3 different frequency response categories. Plus or minus 3 dB. It has good amplitude and the largest frequency response. Plus or minus 10%. It has a better amplitude resolution and a medium frequency response. And plus or minus 5% has the best amplitude resolution but the smallest frequency response. And I've charted that for us so that you can see that on the plus and minus 3 dB, it goes from the min to the max limits that are usable, but it also has the largest variation in amplitude. So plus or minus 3 dB, and so we'd have quite a bit of variation here at the higher end, and then you can see that it rolls off at the lower end. On plus or minus 10%, we tighten up on the amplitude a little, but we also lose low frequency and we lose high frequency response to keep that amplitude tighter. And on plus or minus 5%, we've got some real tight amplitude tolerances, but again, we've given away frequency on the low end and on the high end. So typically, when we're working in the field, when we're purchasing accelerometers, we use the plus or minus 3 dB range, and we try to work within that. And because we're running a program that usually counts on us trending our data, we're not worried about these minor inconsistencies with the amplitude, because in the trend it's always being accounted for. If you're launching the space shuttle, you need to be very nervous about things like this, but we're generally not doing that. So since we're using the trend to drive our condition monitoring program and we're relying on that trend, you're really looking for a change of something to double or 2.5 times in amplitude, and then you need to be very concerned. This dynamic range can trip you up a little bit. And you know, we looked at some sensors here that have 50 Gs of dynamic range, which means at 100 millivolts per G they'd have a plus or minus 5 volt AC output. And that sounds nice, but it's also dependent on your power supply. So here I have a power supply that only puts out 18 volts, and that's represented by this red line. And my bias voltage is right in the center. It's at 12 volts DC, so my bias voltage is centered right where it should be. And my AC signal, plus or minus 5 volts AC, nicely rides around my bias voltage, and it doesn't exceed my power supply voltage, nor does it exceed 0 volts. So this is a very happy sensor here. Even at its maximum vibration, everything's working well. If we go over here, and if my power supply remains at 18 volts, as indicated by the red line, but my bias voltage now has come up to 14 volts DC, well, now I don't have room for my positive 5 volt peak, because peak to peak the signal is 9 to 19 volts. And I only have an 18 volt power supply. So I have clipped the positive peak on this signal. This is going to cause a lot of problems. The first thing that's happening is I'm saturated here. So I cannot get anything more out of this sensor. And that saturation, it's going to do a couple of things. It's going to show you some ski slope in that FFT. And then you're also likely to see some harmonics because you've clipped off the top of this sine wave. So you're fine on the negative portion of the sine wave, but because of this power supply limitation, you've clipped the top of it. And the only thing that happened here is the bias voltage moved to its upper limit, but the power supply didn't change. On this last segment, I've increased the power supply to 24 volts DC. And that's a little more typical of what you'll find, provided you're not using one of the older battery-operated supplies. If you've got your data collector, your condition monitoring system, 24 volts is fairly typical. I've put my bias voltage back in the center of the range at 12 volts DC, and I've gone with an 80G sensor providing plus or minus 8 volts AC. So here you can see that, again, I've got a very happy sensor. I'm swinging from 4 to 20 volts, my min to max vibration, and I'm not clipping anything off. So be a little, recognize that you can clip a signal because your power supply voltage is too low, and we don't really want to get in that position. So on this chart, based on the sensitivity of our sensors here, times the dynamic range that they produce, and the voltage output for the vibration, I've listed the power supply, and you should have these equal or greater than the listing here. So I would always like to see a power supply that's greater than or equal to 20 volts DC. And if I've got one of these 80G sensors, well, now I need to have something that's greater than or equal to 24 volts DC. So I don't want to clip because I'm limiting the power supply. We've got a lot of wiring that's available, and this is probably a whole webinar on its own. Just briefly, different wires are produced, or different cables are produced based on the application, whether it's hot and cold, dry and wet, or chemicals have become a big player as more and more things go online. So a tremendous amount of different cabling is available, and a lot of that's been driven by the chemicals that we're encountering. One thing that is true with every cable, inside of this cable you have a shield. It could be a foil shield or it could be a braided shield. That shield's there again to protect you against electrical noise. However, it's not just the shield and the protection it offers. You have to take that shield drain wire and you have to take it to an earth ground at the point of data collection. It's very important that you get that to an earth ground so that you can take that noise away and bleed it off to earth. And then naturally you have your positive conductor and your common conductor here shown as the red and the black wire. But very important to get that shield drain wire grounded at the point of data collection. Remember, we've got the sensor isolated, so we've got to ground the data collection end. Here's your single axis sensor. You can see the shield drain wire here being taken to earth ground. This IEPE power supply that's denoted here by the 18 to 30 volt DC battery, the diode, and the coupling capacitor, that's built into your data collectors and your condition monitoring systems today. So you have these already built in, and you're just going to use this power supply to not only power the sensor, but to also measure the vibration. And that coupling capacitor, that decouples the DC bias voltage, so only the AC vibration is measured by your data collector. Our triaxial sensor, it's simply 3 power supplies like we just looked at. So channel 1, channel 2, channel 3, or X, Y, and Z. So simply 3 power supplies powering the 3 sensing elements inside the triaxial sensor. Vibration and temperature sensors, a dual output sensor. We use the IEPE power supply inside your data collector to power this sensor. So this will power the sensor. It will also measure the vibration. So typical of any accelerometer, we're powering it, and we're measuring the vibration. Also, we have a small integrated circuit inside this accelerometer that measures the temperature, 10 millivolts per degree C. And this is simply a DC voltage output. So you have to have the power turned on to the vibration side of the sensor so that you can measure the DC temperature on pins C and B. So simply 10 millivolts per degree C DC. Vibration-wise, these sensors are available at 10 millivolts per G, 100 millivolts per G, and 500 millivolts per G. We've got these great wiring guide. It covers not only the CTC wiring, but also the Pro 4 to 20 milliamp wiring. Again, this is something that Matt can provide to you simply by asking. So please go ahead and ask Matt for not only the industrial accelerometers, but the wiring guides. We worked long and hard on these, and they're really good reference materials.
Thanks, Jack. It's Matt speaking here. I'll load them up on the download section of our website. So
okay.
Nice and easily. Just at this point, Jack and guys, what we might quickly do is we're just about to talk about the mounting side of things. I've just got a poll question that I'm just going to launch out here. And I'd just like you to quickly answer this poll for us so we can get an idea what sort of mounting we're all looking at for the majority of our permanently installed sensors. So what you'll see here is you should get a question appearing on your screen now. So if you can just see which of those mounting techniques is most applicable to you, and the submit your answer, and then we'll see what the answers reveal. I'll give everyone about 30 seconds or so to do that. Okay, we're about done. I think everyone's voted now, guys. So let me just close that poll and have a look at what the answers are. And share the results with everyone. And you can see that about a third of people were exclusively drilling and tapping. We've got a third or so who are doing drill and tap and a few epoxies. But there's still a reasonable amount of people who are doing mainly epoxies and mainly or exclusively epoxies. So that's interesting, Jack. I suppose I expected epoxy to be a little bit lower with the group. So that's kind of interesting. That's consistent, Jack, with what you'd normally find?
We find a lot of people are using epoxy, yes.
Yeah, okay.
Yeah, and in some applications it's very good, and some others I would say not so good.
Yeah, okay. And where would you say, Jack, it's most attractive to people, or perhaps I'll let you put that in your slides?
I think just a clean or easy areas. When you get into paper mills and steel mills and up in those wind turbines, it's not such a good idea.
Yeah, sure. All right, Jack, well, I'll let you carry on and give us some more detail on the mounting then, please.
All right. We have a really big range of mounting hardware, and I applaud those of you that are drilling and tapping, because that's really the best possible mounting system you have, not only for reliability but also for frequency response, because you've not put anything between the sensor and the machine. And when you look at all these items that are on the screen here, well, every one of them adds mass and reduces stiffness. And when you put one of these between the interface of the sensor and the machine, you're going to change the frequency response. And the trick there is knowing how much. So we have this chart, and I really I hesitate to even talk about this probe tip business, or stinger, some people might call it, or pointer. It has no really contact point, no transmission. It adds a lot of mass, and there's almost no stiffness here. So you can take a very good accelerometer and you can attach this probe tip to it, and all of a sudden you only have 500 hertz of frequency response. What do I see it used for that makes any sense at all? Possibly if you've got to slip by a guard or to get into some real tight spot where nothing else is working for you. So generally speaking, try to avoid those unless it's a method of last resort. This is the biggie for the portable monitoring guys, the curved surface or 2-bar magnet. This is the winner there for all the portable data acquisition people. 2,000 hertz, and I'll show you. I've actually got an example of why you only get 2,000 hertz there, and it's just a good look at what happens when you put something between the sensor and the machine. This is a quick connect. Probably has a much better application when used with a triaxial sensor, but if you're doing rapid roll changes or something, this is a good mounting method for rapid roll change, because you don't have to mess with the wiring. You just do the quick connect, drop it. When the new roll comes in, you hit it with a new quick connect, and you're connected again. You don't mess with the wiring at all. The flat magnet with a mounting target, this is a much better portable measurement method. You get almost 10,000 hertz if you've got a nice flat target to attach that magnet to. It doesn't have a lot of mass, but it does have a lot of stiffness and contact area. So good transmission here, good frequency response, and still portable. Here's our epoxy pads. When you're doing epoxy mounting, cleanliness is number one. No paint, no rust, no oil. You've got to have a clean, flat, dry surface, and that'll help that epoxy really take hold and stick. And then the very, very best you can do is stud mounted. And like I said, you've got a good, reliable connection here, as well as nothing between the sensor and the machine. So you get the maximum response of the sensor if you do this. Here's an example of losing data. You don't want to lose data because of your mounting method. It could be critical to you. You know, you're going to wonder, why did my machines fail? The vibration looked really good. Well, the vibration looked really good because the stinger or the probe tip wasn't able to measure the high frequencies. You can see here that they're missing. At the same time, if we measure the same machine, same position with a two-pole magnet, you can see that we picked up the mid-frequencies, but the high frequencies were still missing. And then when we came back with our flat magnet and our mounting target, we were able to see the entire story. We got to see all the, whoops, sorry about that. We got to see all the vibration, not only the low vibration, but the mid frequencies and the high frequencies. So be very careful with your mounting methods that you're not losing valuable vibration data. Know that when you put something between the sensor and the machine, that it's going to affect the frequency response, and it's not going to make it better, it's going to make it worse every time. Here's the high frequency response of a AC 102 100 millivolt per G standard general purpose sensor stud mounted on our shaker system. So I've got it stud mounted, and we're sweeping from 10 hertz to 20,000 hertz. And this is still within 1 dB. This is a really good response. So we've got this great response, we've got a nice sensor, and then we're going to attach a nice curved surface 2-bar magnet to it and repeat this test. And what happens is you lower the resonant frequency to around 3.7 kilohertz or 4 kilohertz, somewhere in that region. Because you've lowered this resonant frequency, your usable frequency range tops out at about 2,000 hertz. And that's due to the natural frequency being equal to 1 over 2 pi times the square root of the stiffness divided by the mass. So we added a magnet and increased the mass, which decreased the frequency, and we decreased the stiffness, which decreased the natural frequency. So this is just kind of a good example of what happens when you get something between the sensor and the machine. You're going to add mass, you're going to decrease stiffness, and the natural frequency moves down, and when that happens, the usable frequency range also deteriorates. Don't be fooled either. It's not the size of the magnet that matters. The different sizes or pull strengths are simply to keep the magnet attached to the machine. So a larger magnet has a larger mass, a smaller magnet has a smaller mass, but they all do about 2,000 hertz. That's on a 2-bar curved surface magnet. Remember, if you want to go with a magnet and a portable data acquisition system, you really want a flat magnet with a mounting target. It'll perform much better, especially for those guys doing peak view, man. That's the way to go. Spot facing for our permanent mounting, we've got to have some tools, because we do have to have a flat surface. So we can use the spot facing tool. It kind of looks like an end mill with a drill bit down the middle of it. We always prefer a right angle drill. And the main reason we prefer that is you tend to get a straighter hole and a flatter surface. You don't get a surface that has an angle to it like this. A lot of us are predominantly right-handed, and if we get a a drill that isn't right angled, just a standard drill that you're pushing on, we'll push harder with our right hand. That's our predominant hand. We push harder with the right hand, and all of a sudden you've got a surface, like I said, that's got a slant to it. So by using a right angle drill like this, you're just pushing straight down on top of the cutting surface, and the other hand is over here just running the trigger. So you have a lot less tendency to get that angle in the spot face. And then, something to clean up the area, we've got to drill and tap it, as shown in the picture here, to get our threads in it. Here's a good example of a top exit sensor. We have a nice spot face surface. We've got our drilled and tapped hole here. We've got our mounting stud, and we're going to bring that sensor right down and mount it onto our spot face surface. Don't be afraid. If you want to, you can put a little bit of Teflon lubricant or something under here. Anything you can do to take the air out of the micro cracks that are in the surface there, that would be a good thing to do, because we always transmit vibration through a solid better than we do through air. And here's our side exit sensor. And I don't know how many of you are aware, but the side exit sensor actually has a foot on it. And the height of that foot's probably only around 2 millimeters. So when we're doing our spot facing, we need to be pretty careful, because if this gets too deep, we wind up putting that side exit sensor in there at a cantilever, because you wind up, the foot's gone down into the hole because it's too deep, and then you're sitting on the edge of the sensor, and all of a sudden you've got air under your sensor. That's never a good thing, not to have a surface contact. So you never want to be able to take, well, for me it would be a $1 bill, and slide in underneath this sensor anywhere. You can see here that we've got a nice spacing, and this foot is right down on the spot face where it should be. So be very careful when you're spot facing for a side exit, because if you go too deep, you're going to get into this cantilevered mode, and you're just not going to get good transmission. And if you need to fix it, well, this is a good time to buy yourself a double-sided mounting stud. Put that mounting stud right into your spot face. Buy a mounting pad that has a through hole. Thread the mounting pad down onto the spot face, and put some epoxy under that mounting pad. Turn it right down into the epoxy, and then bring your side exit sensor down on top of the mounting pad. And that'll fix the problem that you've gone too deep here. You'll get that epoxy in there making good contact, and you'll transmit right up through the mounting pad into the sensor. So that's a real nice fix if you've gotten that spot face too deep. Looking at our triaxial sensor, again, we do have a foot on this. It's a little more forgiving. You might get about 3 millimeters here. So again, we're going to bring that down into our spot face for permanent mounting, and put that right in position there. Also note that when you're permanently mounting a Trax, it's up to you to orient the axis in the correct directions. For portable triaxial mounting, if you're using a Trax as a portable sensor, I really prefer having the quick disconnect, because it's keyed to the sensor and it's keyed to the stud that it mounts on. So in this manner, you can never mount this in a different orientation. So once you establish the orientation of this sensor, it doesn't matter who's taking the data, it will always mount in the same orientation. And with a triaxial sensor, it's very easy to mess up the X and Y axis in your database. So be very careful with that. And here is a triaxial accelerometer mounted onto a motor. And note that this is mounted in the axial direction. Remember, we'd like to have our best mounting in what would be our highest frequency direction. So we want the best mounting for the best frequency response. And typically, the axial direction will give the highest frequency. and then we will use the Y and the X, to sense the radial vibration. So always try to get this mounted in the axial direction, and always try to get it in the load zone still. Here's our adhesive pads. Again, we're going to need a flat surface, whether it's a spot face or if you're just taking a surface down with a grinder or a file, you still need to have that flat surface. And as I mentioned, it has to be clean, clean, clean. There's no substitute for cleanliness here. If you don't get it clean, this epoxy is not going to hold for you. So get everything cleaned up and dried up. Get your epoxy in here and set this in place and hold it in place either with some duct tape or a bungee cord or something like this until this epoxy can set up and dry. We'd offer mounting pads with threaded holes. We'd offer mounting pads with integral studs, or just mounting pads for magnet mounts. So several different options, diameters, and configurations in the mounting pads for epoxy mounting. We also offer motor fin mounts. These come in about 4 different sizes. Very good for getting into these valleys of these cooling fins on motors. You can see one that's actually been physically epoxied into this motor here. This is incorrect. You do not want the fin mount probe resting on top of the cooling fins. The idea here is to get the fin mount probe to rest on the casing of the motor. So you're trying to get that bearing to transmit the vibration up through the casing and not get involved with these fins, which have some of their own frequency components to them due to their construction. So try to get the fin mount probe put into the casing of the machine, then fill the sidewalls with epoxy, having this air gap here above the fins. We also make grease fitting adapters, so you can remove the existing grease fittings in the machines. You can install the adapter. You still get to grease the machine through the excuse me, 90-degree grease fitting. The biggest application we see for these is in hazardous areas. A lot of the requirements for hazardous areas say you have to have a conductive mechanical mount, so that eliminates any epoxy. It eliminates any magnets. These are very easy because you can remove those existing grease fittings. You also run into manufacturers of explosion-proof motors and things that say if you penetrate the motor, you may void the warranty. This is a way to get that connection without any issues. So look for these. They come in both the standard grease fitting and the button head. Since 1995, CTC has offered an unconditional lifetime warranty for any CTC labeled product. Doesn't matter what happens to it. We want to see it when it comes back, so possibly we can improve it and prevent it. But we do have an unconditional lifetime warranty, and we will either repair or replace that product at no charge except for the cost of shipping. So that would end my presentation for today, and if we have questions, it would be a good time to take them, and I will say thank you very much for spending time with us.
Thanks, Jack. We've got a couple of questions if you wouldn't mind. Firstly, Heinrich asked about some recommendation on the best type of epoxy that we should be using, which is a good question.
Yes, okay. If you've got a very, very nice surface and a good finish on that surface, we can get away with the two-part aerosol type epoxies where we just let them dry for a second and then put them together. If the surface is a little roughed up and kind of scratchy and things like that, you're probably better off using that two-part mixing epoxy that kind of looks like paste, and putting that in there because that's a better gap-filling epoxy.
thanks. And thanks, Jeremy had that same question as well. Just on that, Jack, quickly, is there any risk of some epoxies that are too flexible? I know some people like the idea of flexible ones because the sensors won't, or the pads won't come off, but I worry about potential attenuation. Is that anything we need to be aware of?
Yeah, because it all deals with the shore hardness of the epoxy, and the softer it gets, the less frequency you'll pass. It's like having a sponge under the sensor, or a piece of damping material, actually. So, you know, if you just think of double-sided foam tape, you'll probably get a 100 hertz frequency response. If you put in a cellophane tape, double-sided, you could probably get a couple thousand hertz out of it.
Yeah. Okay.
So, you know, you've got to keep the shore hardness way up there to get the good transmission.
The metal epoxies assist at all, Jack?
Yeah, I really like. There's a titanium epoxy out there. It's pretty expensive. I really like that. It's actually machinable, I think, in about 4 hours. It works really well. Just be aware that it is not conductive, as strange as that may seem.
Okay. All right. So metal one's a good idea. Good.
Yep.
A question that we quite commonly get, Jack, how do we minimise the risk of ending up with electrical interference, going out and finding we've got dreaded line frequency peaks in our spectrum from interference after we've installed our sensors? What are the key things we need to be aware of, Jack?
Well, the sensor should be isolated to prevent that ground loop. And the other thing would be taking the shield drain wire to an earth ground as much as possible to protect and get that noise off the wiring. And also, you really shouldn't be mixing the low voltage sensor signals with the high voltage power signals. Probably the best example of that today is in your wind turbines. Nobody is coming down tower with vibration sensor signals simply because you have your power cables running down tower. So, you know, vibration is usually done via Ethernet or fiber optic transmission from the cell down to the operating control room.
Sure. And Jack, as we step up from mains low voltage here, which is 240, obviously up to our 3.3s and our 6.6 kVs and like, we've got to be more and more aware of the distance. Is that's basically it?
Yes, and that's why we get into so much of twisted shielded pairing things, because you twist the wire, it tries to repel the interference,
okay,
as well as the shielding. You know, the best thing is try to stay away from it, or get the low voltage wires running in conduits, things of this nature. Should also be aware that, you know, you've talked about electrical interference. You also have electromagnetic interference. Inside of that sensor, that mass which is acting on the ceramic, that is non-magnetic. That is high-grade stainless steel with no carbon in it. So okay, we won't get any pull on the mass from the magnetism.
Oh, okay.
Yeah.
Those big, strong magnets so close by.
Yeah.
Yeah, okay. Good. And one more question I've got here for you, Jack, is recommended couplers to improve transmission. You mentioned Teflon lubricant.
Yes. Always anything, even a thin coating of oil, if you can get that underneath the sensor when you mount it. The idea there is that those micro cracks have air in them, and they'll never transmit as well as a solid will. I would say, you know, you could put a little epoxy under there, but that just kind of adds to a problem if you're trying to remove that sensor, because it'll get in the threads and stuff on you. So you're better off with a little bit of Teflon lube or a little bit of oil or something there, just to sock that sensor down on top of.
Yep. Okay. No problem. Okay. Well, we're not getting any more questions coming through. So, Jack, well, thank you again for your time, and probably let you go and get wrapped up and ready for bed in New York. And,
yes. Thank everyone for joining us today.
Yeah. And thank you very much to everyone who's joined us today. I have recorded this, guys, so we'll have this up on our website. If I can't get it this afternoon, it'll be up tomorrow. And I'll make sure to email everyone who's attended with both the link to the recording and secondly, the link to those nice wiring guides that Jack mentioned. So thank you again, everybody, and have a nice evening, morning,